Good morning or good afternoon, depending on where you are in the country. My name is Trevor Boucher. I am the social media committee member and webinar team member that's going to be your host today for the August installment of the NWA's webinar series. So I'm particularly excited to be talking with you guys today and getting the opportunity to introduce you to two good friends of mine from back when I was at Texas Tech University. Two really good friends of mine, Dr. Tanya Brown-Giammanco and Dr. Ian Giammanco, that work at IBHS. And you may have heard of IBHS, especially on social media, with some of the amazing hail work and some of the science that's been coming out of that area. We're going to have an opportunity to actually see some of that behind the scenes and then get to know two of the field researchers that are there leading that charge at IBHS. So everybody kind of knows me and probably doesn't want to hear from me. They're here to listen about the really cool hail science we're about to hear. So I was going to just hand it off to you guys and wanted to say thank you for being here and being part of our webinar. But yeah, tell us all about what your story is all about and what you guys are doing there at IBHS.
All right, well, thank you so much for having us. We're excited to present to you. People may or may not know about our organization and about us as individuals. You can probably tell from our last name and the fact that we're sitting together in a room with no masks that we are a married couple. Between the two of us, we have 3 atmospheric science degrees, 3 engineering degrees. I won't tell you who has more of which one, but it's not an even split. We have 32 years of combined field work, and we work for an organization that is a nonprofit that works on behalf of the insurance industry to help people understand how natural hazards damage buildings and what we can do about it to prevent damage, to prevent injuries, to prevent losses. So we've been working at IBHS. I've been there just over 10 years. We built a research center in 2010, which is where I first started. And we've been putting buildings to the test ever since. So we'll talk to you about the hail hazard, some of the work that we're doing both in the laboratory and in the field. And you'll really see that corny. Not only are we partners in life, but we're partners in science too. My work feeds off of his very much so. So you'll kind of see our story as we go along as well. All right, to start things out, hailstorms basically tell us that we don't build with hail in mind. As you think about the way that homes and businesses and buildings and everything is put together, even cars are put together, they're not put together to resist hail. They're just not. The materials are not intended to resist hail. They're not intended to stand up to hail. Really, they're not intended to survive hail at all. Now, they do in terms of still being there. I mean, hail's not going to blow something away like a tornado will, but hail causes a huge amount of damage. On an annual basis, hail accounts for about $10 billion, $11 billion worth of damage in a single year. So while it's not on the same level as a very big, intense hurricane, we don't get hurricanes every year, but we pretty much get $10 billion worth of hail every single year. And you hardly ever hear about people being injured or killed by hail. It's super rare. Hail is very much a financial problem. People are spending a lot of money to fix their cars and their homes and their businesses after a hailstorm. And it's not addressed in building codes either. So as we take a little bit of look about losses, I think a lot of people would be surprised to know that hail does account for the biggest percentage of severe convective storm losses from the insured standpoint. Obviously, the media attention, the loss of life, those kinds of things are definitely bigger in the wind and tornado space. There's no doubt about it. But the number of those kind of events are really small compared to the number of damaging hail events. So hail, from a financial standpoint, really pulls a big portion of the losses. As we look at what causes damage, you think about hail, it's obviously falling from above. So guess what it hits first, generally speaking? It's the roof. The roof overwhelmingly sees the most amount of damage in hailstorms. If you have wind-driven rain, you can also get damage to siding, windows, things like that. But generally speaking, the overwhelming majority is focused on the roof. So from a what can we do about this hazard standpoint, that's where we spend the overwhelming majority of our time researching things in the lab. So to kind of walk you through what we're going to talk about today, there's a couple of key pieces. First, we're going to highlight some of the existing test methods for building materials, specifically roofing materials. We'll talk about some of the gaps in knowledge associated with those and why we needed to launch the field study in order to fill those kind of gaps. We'll also talk about how we've taken the information that we've learned from the field and translated it into a brand new laboratory testing method. So we'll talk about the technology that got us there and what the new testing method entails, and about how we've actually gone out and rated products now using this new test methodology. So to start us out on existing hail impact test methods, this is really the only material that currently has a hail test. It's for roofing materials, and it's based on kinetic energy theory. So the simple high school physics, 1/2 = mv squared. The kinetic energy is calculated in these test methods from assuming a spherical hailstone of a given diameter with a mass that's exactly equivalent to pure ice. Couple of problems there. Hailstones are not spherical, so they have different aerodynamics, different terminal velocities. So right off the bat, you've got an error in the kinetic energy calculation. And the mass is not equivalent to that of pure ice. Hailstones are actually less massive or lower in mass than pure ice, pure water ice. So you've got two factors that are both not quite right in the calculation of kinetic energy. So right off the bat, you've got a challenge there. As we look a little bit more into this problem, this is a model, a 3D model of the very first hailstone that we ever scanned in the field. Ian will talk a little bit more about that. But there she is. We call her Elsa. She came around the time of Frozen. So there's where the name came from. But you can see that it doesn't have the same spherical properties. Ian's going to play a video for me. You'll see a round sphere drop in over it. And what I want you to kind of notice is the amount of volume that's not there. If we say that this stone has a max diameter, let's just call it 1 for the sake of argument, 1 inch. A 1-inch sphere has way more mass than this 1-inch hailstone. All that gray space is place where the hail doesn't actually have mass. Plus, you can imagine that this thing, because of its a little bit more awkward shape, it doesn't fall as smoothly and as simply as a spherical hailstone would. So we know we got some issues there. As we look at the first standard test method, it's a test method written by Underwriters Laboratory. It's called UL 2218. Most of the places that would offer a discount for a good roofing product or a hail resistant, an impact resistant roofing product would refer to the UL 2218 method. It's been around since the 1990s, late 1990s. And there are products that are rated to this available in the market. On the good side, it's repeatable, it's easy, I can do it by myself. It's not a hard test to run at all. We can knock through probably 6 or 7 panels on that test a day with no problem from the test side of things. The rating's a little bit longer, but leaving that aside, it's pretty simple. On the con side, I talked a little bit already about the physics being wrong. The mass is wrong, the aerodynamics are wrong, which means the velocity is wrong. The kinetic energies are too high. The speeds are too high, the mass are too high, so the kinetic energy is too high. You'll see in the picture that's there on the upper side of the screen, the telltale sign of this test is crushed granules on the surface of the shingle. That doesn't happen with real hail. Real hail is not hard enough, not tough enough to crush granules like that. It can knock granules out. It can, cause a crack or something in the shingle. It can't crush granules like that. That pulverized look, that's not real. That's not what real hail does. So it doesn't quite match the physics that a real hailstone would match. We're also only looking at the back side of the shingle to say yes or no, there's a crack, and it's a binary answer. It's either yes or no. So from a product differentiation standpoint, it doesn't have a good ability to do that. Any product that gets any kind of crack fails the test. It doesn't matter how severe the crack is, how many cracks there are, it's just a single crack and it's over. You get a failing rating. On the FM side of things, this is a test developed by Factory Mutual, which is an insurance company, and they have a lab associated with them. They do use ice, but they use pure water ice. So it's literally water squirted into a mold, put in a freezer. We bought ours from Lowe's, so it's just a regular run-of-the-mill freezer, nothing special about it. So it gets a little bit more in the right direction. Obviously, ice matches the impact of hail much more than a steel ball does, but it still got some problems. It still has a yes, no, pass, fail rating if there's a crack or not. And the damage that it produces, while it's the right kind of damage, it causes granule loss, it causes cracks. It's way too severe because you're using a very fast speed and a very heavy ice ball compared to real hail. So of course you get damage that's really too severe compared to what we see on brand new shingles out in the real world. And this just kind of illustrates it a little bit more. In these two test methods, the only thing that matters is yes, no, there's a crack. But you can see that there's pretty big differentiation between kinds of cracks and how bad they are. We've got the epic failures where it's like, I can see that, I can see that from the street. I don't even need to get on a ladder. Those are bad. Those are probably going to let water in between the layers, which could be problematic. Versus those that are on the right, the not so bad ones, if I didn't circle those, and even though I have circled them, you still may not even be able to see the crack. They're really, really hard to see. In the test methods as they are now, those are treated the same, but we feel pretty strongly that the one on the right is way less concerning from a damage perspective to the home than something that's on the left. So as we went through these test methods, we found some of the things that we liked and some of the things that we didn't like. And what we realized was that we needed to attack this problem a little bit differently. We were still using the same kinetic energy kind of theory, but we needed more information about the aerodynamics of hailstones and about the shape, the size, the hardness of hailstones, the hailstone characteristics themselves. Pure water ice in your run-of-the-mill freezer is not cutting it. So we wanted to be able to go out into the field and get additional data to help us perfect this in a laboratory setting.
Yeah, so in comes field research. We needed to understand what are the characteristics about hail that we needed to duplicate in the lab. Tanya talked about the UL test, so that's a steel ball, highly, highly focused. That steel ball does not give when it hits something like a shingle. FM went with the pure ice ball. The problem is, think about all those ice cubes you pull out of your freezer and those expansion cracks. Highly variable in the strength of ice that comes out of that test. So it's not repeatable. So stone number 4 is not the same as hailstone number 8 that you might shoot at a panel, or 128 down the road if you're testing. So we need to, one, understand what do we need to measure? What do we have to figure out? And how do we do it in the lab so it's consistent and repeatable? So the first step was field research. As Trevor kind of mentioned, we go back all the way to Texas Tech days. And one of the critical things about the research program at Tech was they kind of drill into you this concept of you can learn a lot just by looking. It's a quote actually from Joanne Simpson. And we take that approach with hail, is what do we need to go look at and how can we learn from making those observations, both in the built environment and the field? So we both participated in many different field programs at Tech, from hurricanes all the way to severe convective storms, the Vortex 2 project. So we knew how to go at least take a stab to execute a field program to get the measurements we actually needed. So kind of looking back, we began in 2012 with the emphasis to try to figure out what properties of hail we need to duplicate in the lab. That's basically density, strength. That controls the impact mode and ultimately controls the type of damage and the modes of damage you would see on the built environment, namely asphalt shingles. So on and on the program goes, and I hope many of you out there follow us on Twitter. It's at IBHS Hail Study. You can kind of see the progression of the program. We went from understanding hailstones, kind of moving ahead to hailstorms, develop in situ instrumentation to capture hail swaths. We've even started looking into environmental characteristics that govern a lot of things about hail, the strength, the concentrations, and figuring out ways to measure them. And Tanya mentioned already 3D laser scanning. It's something that we're very proud of, being able to pioneer that type of measurement system to really get detailed understanding of hailstones. So when we began, like any field project, you go with the statement, this should be pretty easy, right? We just got to go measure hail. We got to do some kind of test to get the strength of it, and we got to get the density of it. Well, like any good field program, it starts with a heck of a lot of logistics at home. You see a couple pictures on the screen of us working in the lab, just getting ready. We're in South Carolina, so we have to get all of our equipment during periods of active severe weather out to essentially the Great Plains, where you can actually go do safe scientific storm chasing and make these critical measurements out in the field. So again, it takes a lot of prep. We have some really big Pelican cases that we pack up equipment in. We actually ship it out So we're forced to kind of use the medium rain forecast to be able to see, are we expecting an active period of severe weather? Really, you're just looking for flow aloft. Is the Gulf of Mexico open? And can you get organized convection? And then we usually spend about 10 days or so, 10 to 14 days total in the field, usually over a couple of different missions. So we kind of work as long as we can for a given period, come back home, and then look to kind of reset ourselves and go to work. Like any field project, it's wrought with the classic hurry up and wait scenario. A couple pictures of us hanging out in a hotel lobby, the world's largest ball of twine in Cawker City, Kansas. That for whatever reason, out of all my field years, I didn't run into it until we did the hail project. All the years at Tech and Vortex 2 never actually stopped, but we decided to stop one day. Lots of field testing. Some of the best work, my old graduate advisor joke, in instrumentation work, some of the best work's done in hotel parking lots. So that's that bottom right image, getting some of our in situ hail impact probes ready to go for the day, along with some students from Penn State. We've had a great partnership with Dr. Matt Cumgen there and his students who've come to the field with us. So they get to experience a field program as well as take that back and do the kind of active application research back at Penn State. So some of the tools we've used over the years, the top left is the device that actually does the compression test. It actually crushes a hailstone. It's a pistol grip. You basically compress it. There's a load cell underneath that little white cap, and it measures the amount of force it takes to fracture that hailstone. It's kind of a proxy for the overall hardness of a given hailstone. Your classic digital caliper, no better tool in the field to get a good hailstone maximum diameter than a good caliper. So those of you who are out there storm spotting, chasing, those kinds of things, get one and get some good hail measurements and make those reports. Very much helps to get good detailed measurements. Tanya mentioned 3D laser scanning. We have a handheld scanner unit that's Ross Maiden up in the top right, scanning the Alabama state record hailstone in near Coleman from a few years ago. And on the bottom right is our hail impact disdrometer. These are in situ probes that we actually deploy out ahead of thunderstorms. I'm a big believer in adaptive observing networks. I kind of joke that they can save the world, but they can make critical measurements where it's not safe for people to be and in mass. We have 18 of these. This builds upon the sticknet concept that Texas Tech deployed during Vortex 2 in the years after, not only in severe convective storms, but also in tropical cyclones too. So I took that and applied it to hail with the design that was done by NASA. Now, one of the things we've been able to do is actually take a look at what are the environmental cues that may play a role in understanding hail strength. So what you're seeing is a map of some of the cases where we had large sample sizes of hailstone strength. And a student intern who is now finishing his master's work, Richard Sirico, did some great work looking at what are the environmental influences of hail strength. So we had these, enough cases with large samples to try to get a handle on, is the environment, the storm scale environment, actually influencing how strong hailstones are. So one of the early things was, in hail, we jumped to instability in CAPE. So we looked at CAPE in the hail growth layer, that -10 to -30 degrees C zone. And he basically didn't find a whole lot. It was no real discernible trend there, a lot of variance. So we're saying, okay, instability, at least in terms of strength, isn't really playing a huge role in terms of governing strength. Well, building upon that work, Laura Shedd, another student intern for us at IBHS from Penn State, also built on this and looked at even supercooled liquid water content from some of the cases. So we segregated all our hail strength data into strong, moderate, and weak kind of categories, and actually found a pretty reasonable correlation there with supercooled liquid water. And that's using the ERA 5 reanalysis data set. Richard also, again, jumping back and forth, these two students did fantastic work. We were able to do some storm relative wind profiles and some kind of idealized photographs, and you're kind of seeing the results of those. And the red is the strong category, where you have a very, very strong hailstone that might even bounce off a roof, or if you look on YouTube, you can probably see hailstones bouncing off asphalt. Those are going to be your really strong hailstones. And we're able to see that there's kind of a strong kind of mid-level inflow layer that helps drive trajectories to get hailstones up in the growth zone and keep them there. There's a lot of really great work going on at Penn State right now in looking at hailstone trajectories and how it affects hail growth as a whole. We kind of piggybacked onto some of that work and looked at strength. And what we're starting to see is that the kinematics themselves are starting to play a bigger role. And we'll touch on that just a little bit later, and also what we can do in terms of radar hail detection in terms of making all these field measurements and what are the uses for that. So over the years, how we've been doing this now, this was the first year since 2012 we weren't able to go to the field. COVID put a stop to that, as well as lots of other field programs out there. But in our database, we've got about 4,100 hailstones that we've cataloged over the years with measurements of multiple dimensions and photographs, 62 different event cases, 151 3D digital models, including the Colorado and Alabama records. We have a quick response team. So for all those Weather Service folks out there, if you think you have a record hail report and you're working and verifying that, we would love to get out and come 3D scan that hailstone to digitize it and save that data for future scientists and for posterity. So please get a hold of us if you have one of those events. The things we found are that hailstone shape is key to aerodynamics. Hailstones don't fall as fast as we actually thought they did. That used to be thought there was this kind of roll off and drag so hailstones could really accelerate. Well, the complex shapes just don't allow that. So we've improved those diameter to kinetic energy relationships. That was work that was done with Andy Heimsfeld at NCAR, published a few years ago, and we updated it with some really cool vertical wind tunnel testing of 3D printed hailstones. And we found that strength is the influence on damage mode. There is differences in damage you see between hard hail, the very strong hailstones, that kind of moderate zone, and the weak, more slushy stuff, like you might expect. Strength and density we also found are not one-to-one. So if you think about all the literature that says hard, dense hail, well, no, that's not exactly right. In fact, we haven't actually found any relationship yet between strength and density, except our sample size is probably not where we would want to be to really publish and push that as hard as we could. But we have not found a one-to-one relationship there. We think the hail growth regimes are what's driving things. So I'm going to play a little bit of a time lapse here. I'm going to hop over. I hope everybody can see it. We'll see how it works through GoToWebinar. There's Brian Wood. Many of you may know Brian. He's come out to the field with us, works for Assurant, which is one of our member companies. And he's been great to have out in the field. We've had a couple other members. And this is just about 30 seconds of what an in-situ deployment might look like. Hailstorm passes over our in-situ instrument, and we're doing our manipulation. We come back, pick up the probe, and off we go. What you don't see there is we would physically measure hail at that location. A little shout out there to Jake Sorber, a former Penn State student. He's actually still at Penn State working on his master's degree, another student intern for us. So lots of student participation. I'll play another video. I hope this plays okay. Again, this is just what those impact probes capture. These is 3 probes in a given storm working kind of north to south through an array that was about 4 miles long. I just picked 3. And you're looking at on the y-axis the maximum estimated hail size from the probe, as well as time on the x-axis. So you can kind of see the different flavors. Probe 103, that top one, bigger hail sizes, that was kind of in the traditional core region. 116 is kind of in the middle there, getting closer to the mesocyclone updraft. And 105 was just maybe a scotch south of the mesocyclone where it passed. So you had some hail that actually wrapped around in the hook feature of this particular case. Just kind of a look at what these instruments actually capture. So really nice detailed look at hail. And getting into some of these measurements, what you can do with this. This is MRMS mesh swath data overlaid with our hail observed or detected maximum hail sizes from a particular case. This is May 18, 2018. We had made 2 separate measurements runs on this one. You can see in the top left of the image and the bottom right. And what we actually find is a lot of these hail products itself overestimate the width of the hail swath. Sometimes these, our instruments are very good at telling us when there wasn't hail at all, which can be just as valuable as finding where those big hailstones are. We could look at this particular case too. This is from Eric, Oklahoma, also in 2018. We have 2 really big hail cases from Eric. Poor town got pummeled 2 years in a row. Again, looking at the MRMS mesh hail swath, and you can kind of hone in. In this particular case, the maximum size picked up by mesh was kind of offset. It had a storm relative left bias. So down on the southern side, we actually saw the biggest hailstones right about where the updraft crossed, which is not quite where mesh tagged it. The MRMS product actually in this particular case did really well on the size, the actual maximum size. It just had a bias on that storm relative left side in this swath. And again, a little bit large in terms of the extent of swath coverage. But again, these are radar-based products. You're dealing with beam height, all those kinds of things, beam spreading, the gridding aspect of the MRMS products. and all those different things. But the data we collect can be used to do those kinds of analyses. So kind of we look ahead to the field program, we've started to work more in understanding the environmental influences on hail, some of the regional differences as we see the kinematics start to matter more. You wonder about the low cape, high shear environments that here in the Southeast that we deal with quite a bit. We've been able to really hone in on aerodynamics using 3D printed hailstones. We put them in vertical wind tunnels to watch the tumbling. In fact, a really cool, we went and did an experiment at the iFly wind tunnel in Denver, and put the replicas of the record hailstones in that tunnel. But one of the neatest things we actually saw was that the lobe structures, once the hailstone's kind of at equilibrium, which would kind of be hovering in the wind tunnel equal to their, essentially the terminal velocity, the lobes actually act like rotors and start to generate lift as the hailstone basically spins like this. It doesn't actually tumble. And it actually rose in the chamber as those lobes generated lift. So you can start to think, these really big record hailstones, maybe there's a little bit of feedback there where as they grow these lobes, they can stay aloft just a little bit longer and grow a little bit bigger. And it was just something to really neat to see, being able to stand there and watch this hailstone essentially kind of levitate in a vertical wind tunnel. We'll continue to map the hail swaths, look at the radar-based products and some of the data, do more to make our data more available to folks. We'll touch a little bit more on some of the operational uses of this as we get to the end of this particular presentation, but I'll turn it back over to Tanya to hop us back to the lab to see where we went in terms of making laboratory hail and pushing the envelope on what we could do.
All right. So couple of key things that we really needed to take our hail study forward. We knew what some of the limitations of the existing test methods were. Our main goal in those first 3 or 4 years in the field study was to get that hail hardness or the compressive strength of hail. We had a hypothesis early on that hard hail would cause more damage than soft hail. And as you look in the literature, you can find lots of references to hard and soft hail, but there's no numbers, there's no quantities, there was nothing for us to target in the lab to try to create what was hard or soft hail. So the key piece of information coming out of the field was that. The aerodynamics also go in, but that was kind of our first big step. And turns out we're right. Turns out that it does make a difference. The hailstone characteristics are purely based on our field data. That 4,000 something hailstone number that we have goes into that development. We do shoot 3 specific kinds of hail. We shoot a hailstone that we call hard bounce. So it's a single ice stone, hits the panel that we're testing and bounces back as a whole sphere. We have another one called hard shatter. In that case, it's going to hit the panel and break into a lot of pieces, and it does not leave a residue on the surface of the shingle. And then the last category is the soft impacts. And those hit the panel, they break into a lot of pieces, but they always leave a trademark kind of snow cone looking residue on the surface. And that's where the hailstone or the ice sphere has actually kind of compressed. It's actually changed itself as opposed to just breaking apart. And those do drive different damage modes. The hard impacts drive more of the cracks and tears and dents. The soft impacts drive more of the very widespread granule loss. And both of those things are important in terms of a roof being able to stand up to hail and continue to keep water off. We want to make sure that we keep the granules on and we keep water out. So that was in the hailstone characteristic side. The impacts configuration, this is just where are we going to hit on the panel. It's a little bit different than what the other methods do, just to try to get a bigger data set, looking at different areas of the shingle. And then the last category is the damage and functionality assessment. So we took a giant step away from yes, no, pass, fail, was there a crack, was there not a crack? And by the way, do I think there's a crack? Does he think there's a crack? Do you think there's a crack? All of that matters. We took a giant step away from that, and it is very much a quantitative assessment at this point. So one of the big challenges that came with this was, okay, now that we know the characteristics of hail that we want to get, how the heck are we going to make it? When we first opened the lab, we didn't have a sink or a refrigerator or a freezer in the lab, and somehow I needed to come up with how to make hail, so I bought some of those things. But what I was doing at the time to adjust the density and to get a little bit of control in the hardness was buying all the seltzer water in the entire town between my house and the lab. And every store, and I wiped out every store multiple times. They couldn't keep up with me. So they probably thought I had a drinking problem with too many gin and tonics. I did not. I was using it in the lab. We have eventually invested in a soda gun like you would have at a restaurant, so that we can make our own seltzer. But we still didn't have a lot of control. In bulk, I could change the density and change the strength, but it wasn't super repeatable. And some of that was some of the issues that Ian mentioned in terms of how to make the ice and molds. At the same time as all this was going on, we were exploring development of this machine that we just call the Hail machine, super original there. But this machine was really intended to give us bulk ice production, so make a whole bunch of stones quickly so that we could do full-scale testing in our laboratory. What we found with this machine was that we could basically create recipes. We could use certain settings on the machine to come up with hard ice or soft ice. We can change the amount of gas that we pump in. So we got away from the restaurant style seltzer gun, and now we're just making it in a big old giant tank and freezing directly from the tank, as opposed to pouring it out of the soda gun. But we can change that setting. We can change how cold we freeze it at. We can change how long we freeze it, how long we thaw it. And we're essentially taking this machine and infusing gas into water. We still use carbon dioxide, so it's still technically kind of a seltzer water. We go through that diffusion process. We pump it into a heat exchanger, extract all the heat out. We can freeze about a 6-foot long rod of ice in about 80 minutes. We do a really quick thaw cycle, just enough to release it and let it slide down the machine. And then we're actually forming the shapes that we want. So we've got heated molds at the end that are forming the spheres as opposed to freezing them in spheres. And what you can see here in the graphics is some of that ring structure that is created in real hailstorms. We can do that in the laboratory. We didn't know we were going to be able to do all these cool things with this machine. We just thought it was preventing us from squirting water into a mold for 4 hours a day times 5 people.
So if you looked at that bottom right image, if I just threw that on Twitter, would you think that is a real hailstone, a cross section of a real hailstone, or something made in the lab? But all these like eureka science moments, it's not eureka. It's like, hey, that's weird. I started calling professors back at Texas Tech, and I know I sent Matt Cumgen at Penn State a text. I think I talked to Eric Bruning at Texas Tech. Like, what is going on with the physics in this heat exchanger system? Now, we don't grow hailstones the way a thunderstorm does, but that's the kind of difference a little bit in engineering to science. We are trying to engineer the output to match those natural hailstones.
Yep. And so we're pretty fortunate to have this machine. In fact, it just got a little brother in the last couple of weeks. We're looking at a smaller version of this. This one's ginormous. It takes up half of a room. We're looking at building a smaller one. We just got the design on site, starting to put it through its paces to make this more available to other labs in the future as a possibility. So the other piece was the damage assessment. We have an internal tool that uses 3D point clouds to create basically a stitch together of the impacts. So we take 13 pictures from different angles. The 3D mesh is executed in the algorithm, and it spits out images that look like this. And of course, there's data behind the images, but this is far more cool to look at. So basically what you're seeing here, the different colors, the greens and the reds, there's not much going on. This is basically picking up the granulated surface. This is a representation of kind of the 3D. So when we say negative, is it kind of below grade, and positive, is it above grade, if you think of it like that. So in this particular impact, there's really not much going on. Versus this one, you can see the visible crack in the luminance image on the left side, but you can also see it on the data side. That big hot spot in the center of the center photo there, that's the dent. There's a big old dent there in the center of this impact sample. And so all of these pixels, we're actually getting numerical values out of these in the background with the algorithm. This just gives you a visual representation. But this shows you the kind of power that you can have from tools like this. This is an artificial intelligence 3D point cloud kind of algorithm. It's custom designed for this particular application. We do it with iPads. You could do it with any kind of photo. It's pretty simple. You just snap the photos, let it do the work. And it has taken us from do I think there's a crack? Do you think there's a crack? To data. There's data behind this now. So I can quantify exactly how bad that dent is and compare it to something else. No more yes, no, pass, fail. We've got data now. And what we've been able to do with that, we published for the very first time manufacturer performance scores by name summer of 2019. So just a little over a year ago. We categorized a set of impact resistant shingles. We looked at how they performed in granuloss, tears, and dents. And you can see kind of what the graphic looks like. This is the way that the scores are displayed. On the website, if you want to check it out, IBHS.org, you can actually see how the shingles performed by brand name. So if you're looking for a new roof and you live in a hail-prone area, pick one of the ones that we rate as good or excellent. Those are the ones that have stood up to our test, that's got better science behind it. Those are the ones that we think are going to give you better performance in the real world. So this was kind of a long path to get us to performance ratings, something that a roofer or a consumer can talk about and say, I want that shingle. I want number 1A because it has really good performance. That was the goal all along with the impact test program. It just took us a really long time to get there, to figure out how the heck do we make these different kinds of ice? How the heck do we capture these different damage quantities? How the heck do we measure hailstones to figure out what the hail strength is and stop relying on hard and soft qualitative from the literature? It took a long time, but we really have changed really the way the manufacturers approach this as well. Since we released those data last summer, we've had one manufacturer pull a product. It's no longer available. It was one that got a poor score on our rating. It's not on there anymore because it doesn't exist. You can't buy it. They replaced it with a product that now gets a good score. We've had other manufacturers not pull products, but have introduced brand new products that are just doing so much better. So it's kind of one of those ask and you shall receive. We want consumers to have better options, and the manufacturers are paying attention, and there are now better options available for your roof out there.
So kind of wrapping us up, a little bit of insights that you as operational meteorologists may care about, that what we've been able to do from our work, both in the field and in the lab, kind of understanding things. One of the analysis that we've done is use a lot of CoCoRaHS hail data. It's a great tool to get beyond just the storm data hail reports, where you can take some of those old hail pad cases, especially from the Colorado hail pad program that's been integrated into CoCoRaHS. In this particular figure, we actually kind of did a spatial analysis looking at the ratios of maximum to minimum hail diameters. And what jumps out is kind of the Front Range High Plains Tornado Alley supercell areas, a little bit of signal for Dixie Alley, showing kind of a larger hail distribution. These cases were actually driven by more smaller hailstones. And when you speculate, do supercells produce wider distributions of hail sizes? Now, there's some evidence through some of the in situ data that actually varies within a swath of hail based on storm relative location. But those measurements made by these citizen science programs are really critical in the private sector. We use them all the time to understand risk and vulnerability, especially on a hazard like hail, that there isn't great observations for. Observing severe weather is crucial for us to understand how to build better and how to get better materials on roofs. This was a little bit of duplicative work. I wanted to look at what Scott Blair found several years ago, where he found kind of a correlation between azimuthal shear, in a particular supercell, and the maximum observed hail size. So these are from IBHS cases. Again, found a similar trend there, that increasing that normalized azimuthal shear often can give you larger hail sizes. There's some variance in there, certainly. But overall, you're kind of looking at the same thing that Scott found several years ago. So we had kind of blended data in that one. We can also take a look, I mentioned already the MRMS mesh product, some of the radar hail detection algorithms that are out there as part of the 88D package, as well as we get into dual pole. We were fiddling a little bit with hail differential reflectivity from the original Depew work, comparing it here to a single radar maximum estimated hail size and the MRMS product. As you can see, in general, those radar detected products overestimate hail sizes typically. The single radar case was up to over an inch in root mean square error. The absolute error came in just under an inch, at least compared to the IBHS cases, all those thunderstorm cases that we've had. Some of the HDR stuff actually underestimates hail size. It's not bad, but again, you got to tune that really, really carefully, and there could be a lot of noise. But we were kind of fiddling with that. You can also do the classic skill score analysis of these products. Again, most of them are actually really good at telling you that hail was actually there most of the time, but you do have a little bit of a false alarm problem, mostly just by the spatial extent of a swath that's a little bit bigger than what's actually there in real life. Looking at the kind of critical success index things, you got MRMS mesh and the new dual pole hydrometeor classification algorithm doing pretty well there. Not a surprise. And then in bias scoring, you get the hydrometeor classification algorithm closest to that #1 mark to not over or under predict, but most in general kind of over predict hail size. Another comparison, this is the new dual pole size classification for one of those Eric, Oklahoma cases. Again, kind of missed some big hail. It got the swath really, really good. And I did a gridding analysis just on that single radar data, and that's from the Frederick 88D. And you can see it did a great job with the swath extent, again, missing on some of that giant hail. We had over 2 3/4 right smack in the middle of this swath, as well as a 2-inch. What we loved about this case, it showed the gradient down on the southern side. You go from like 2-inch kind of giant hail that's going to really pummel a roof down to 3/4 inch in less than like 3/4 of a mile. It was probably in the few hundred yards if you actually were mapping that entire gradient. So really tight gradient there between very damaging hail to subsevere to no hail at all. And the dual pole product here actually did pretty well. Another piece we've also used CoCoRaHS data for is looking at damage thresholds too. There's a way for citizen scientists to actually enter in damage observations. So we get to look at thresholds of visible damage to like homeowners, just like you and I, how they would actually see the damage on their roof. So again, you see damage to houses, windows, roofs, often start at that 1.5 to 1 3/4, again with some variance there. And we were even able to look at impact angle from some of that data. So the CoCoRaHS stuff was highly valuable. And I'll let Tanya kind of wrap it up with some of the building damage insights to bring us home here as we wrap up our presentation.
All right. So we said early on in the presentation, damage from hailstorms is estimated at about 10 billion. This will be our 14th straight year of meeting that number. Comparing back to, when we first kind of started in this, it was unheard of to see $1 billion loss very frequently in an individual year. And now we're in the $10 billion range. The roof is the most likely thing to be damaged. Other things can be damaged, but again, thinking about the vertical nature of hail, it's generally the roof unless you have very significant wind-driven hail, like you do in the picture here. Older materials are more likely to be damaged than new materials. So as you're out and about after a storm or during a storm, pay attention to those kind of things. Something that shows a lot of damage may be a fair bit older. Materials just become more brittle with time. I mean, if you think about plastics and things like that, you get that they are more prone to crack. They're stiffer. They don't have the kind of give that they do when they're brand new. One of our asks here, the meteorological community has a huge ability to reach the public. For the vast majority of people, the only science that they may get in their day is from their TV meteorologist. If you're out doing a storm damage survey or you're part of the weather service, whatever the case may be, it is actually possible to build better. It is actually possible to choose roofing materials that will better stand up to hail. So we're asking for your help. Help us amplify this message. When you're replacing a storm damaged roof, you really want to consider one that has better performance. So you can choose an impact resistant class 4 rated roof cover. That's if you're going with a generic roof. If you're going with an asphalt shingle, choose one of the ones that we have rated as good or excellent. That goes better than the UL 2218 or FM test that we talked about. If you're choosing something that's not shingles, that's still the best science that's out there right now, but give us a couple more years and we'll see if we change that too. But if you're choosing shingles, please help people understand that they can choose something rated good or excellent from our test and give themselves a better chance the next go around. And many of those roofing products in many jurisdictions qualify for an insurance discount. So they may be a little bit more upfront, but you can get some definite savings in monthly premiums from insurance. So please help us get the information out. You can build better. We know how to do it. There's information on our website to do that. And I'm talking about this particularly with regards to hail, since that's our topic for today. But we also have a program called Fortified that's basically how to all around build your house better, particularly for wind hazards. So beyond hail, there's better ways to build for wind too. And all that information's on our website as well.
If we think about the future of what is a weather-ready nation, you know, in the meteorological community, we talk about hazard communication, forecast, warning, decision-making, making sure the general public digests that weather information. But we strongly believe building better is, and that message is also part of it. That's going to stop the avoidable losses, the disruption that comes with severe weather that happens every single year. We all, you know, you and I, we sit here and watch this. And to be honest now, when I watch a catastrophe unfold, a bad tornado event or even a landfalling hurricane, I go from kind of struggling emotionally to just getting angry because I know we can do better. And in most cases, it's not even cost prohibitive. We had one of our fortified homes that was built by Habitat for Humanity, basically take it on the nose from Michael. And you wouldn't know that there was a hurricane unless you looked at the surrounding structures. We know how to do this. And we are learning the ways in the areas that we don't to do this. So if you think about the future of what a weather-ready United States looks like, it's incorporating all of this, the meteorological information, the better building science. We can stop that damage and the disruption that comes with severe weather. We're learning how to do it. We just have to find the will.
All right. If you want to get more information, all of our Twitter information's up there. We're pretty active in disaster safety. Ian's more active than me. And then during the field project, we're super active on IBHS hail study. So we'll go ahead and turn it back over to you, Trev.
Yeah, I actually have a few questions myself to follow up with, but before we get to mine, we had some that came across GoToWebinar. Some of the names you may actually recognize. The first one coming from Mr. Mike Texter, actually, somebody we know from our Vortex 2 days. But he asked, has there been any work done in different roof shapes versus hail damage, and how do they correlate? He was curious if there are best practices for angles to minimize impact.
With hailstone shape, while we have the ability to make different hailstone shapes right now, we can just change out the molds on the front of our hail machine to make those. We don't have a great way to shoot them to make sure that they come out consistently and don't get different tumbling between stones. So from a testing perspective, we really haven't looked at the effects of shape. It's something that's kind of on our radar. We still have a fair bit of work we can do with spherical shapes, so we'll keep going after that. But that is a place that we hope to look more into things. On the building impact angle side of things, one of the places that we may start exploring in the next, call it 2 years or so, is impact resistance of siding. Because if you get a little bit of an angle there, I mean, you saw the picture, and if anybody's paid attention to some of the Calgary storms that have gone on this year in Canada, you just see the siding shredded everywhere. So trying to understand what kinds of siding materials really are best for hail-prone areas is an area that I suspect we'll dip our toe into in the not too distant future. The overwhelming majority of hail is going to be more vertically falling, but once you start getting into that wind-driven, it definitely becomes problematic. And Ian has found, I think it was through the CoCoRaHS data, right, that showed the impact angle gets.
Yeah, in the CoCoRaHS data, you could actually, there was a field where users could enter impact angle, and you can discern it from hail pads, the actual stretching of the impact marks. In general, it was about 20 degrees off of vertical. However, if you looked at how that changed with maximum hail size, it actually got less vertical as hailstones get bigger. Now, intuitively, that's okay. The thunderstorms, the supercells that produce really big hail, we know they're going to produce strong outflow winds too. That's what that signal is telling us. Now, at that 20 degrees off of vertical, yeah, a lower slope, 2 on 12, 412 roof is going to take a direct impact. You're going to have the most concentrated impact. But you think about roof slopes and impact angles, all you're doing is stretching out that impact over a larger surface area. Now, okay, you might reduce, you could envision it might reduce some of the cracking problems, but it could end up exacerbating the granule loss problem by essentially stretching that impact and scraping off more granules, because you've essentially subjected of a larger surface area to kind of a weirder energetics as that impact kind of comes in more at an angle. And as Tanya mentioned, the siding component, you'll probably see some stuff out of IBHS in the coming years as we start to look at wall covers and get a better handle on what should be the best practices there.
Sounds good. Yeah, I think one of the things he was talking about is roof angle itself. So if you end up having like a very steep roof that's a little bit more of a point, that would have kind of a different effect, obviously, than something that's flatter in the shingle world too. So it kind of depends on the impact angle there.
Yes, if you have more vertically falling, the steeper roofs are going to be better because you'll get more of the glancing blows.
And I should say, like, if you look at everybody now out there with slow-mo cell phone cameras, it's actually a great tool. And Julian Bremelo from Environment Canada is one of the people who kind of brought some videos to my attention where you can actually see in the slow motion video, there's various impact angles going on within just one spot within a hail event, which is really, really interesting. So there's potentially a lot more chaotic motions going on that we even really understand right now. So I'd say from a science understanding, we're probably working in the noise. We just don't have enough knowledge yet to be able to give something that would have a actual meaning at this point. And hi, Mike, it's good to, thank you for asking that question.
Okay, so on the topic of people you know who are asking questions, our next one comes from one Dr. Scott Gunter. And he asked, have you seen the same storm produce hail with sharply different hail characteristics? And how would you separate or assess the storm environment to play a factor in that?
Oh, Scott, that's a really good one. And yes, we have seen some variance in strength. It's something we didn't think about until recently. We had actually retired the crushers 2 years ago. We thought we wouldn't come back to strength research. And then Richard did his work and Laura did hers. And it was like, oh my goodness, the environment's playing a pretty big role at the storm scale level. Some of the work that Matt Cummings is doing in storm scale modeling is really starting to hit on this, that hail, the supercells producing hail, the way the wind field's interacting with them and the hail trajectories actually do change over the course of a storm's life. Him and Kelly Lombardo published a really, really good paper. I would encourage anybody to go look at it, and can show these kind of pulses in hail production and growth. We believe that same thing happens in strength. We just hadn't at the time really knew much to guide experimental plans. So that's something we do want to look at. And as there's kind of discussion out there of a larger multi-agency field campaign in the coming years to study hail. There hasn't been one since the 70s in the National Hail Research Experiment. These are the things we want to look at. So Scott, you're kind of on the money there, that a single supercell may produce different quote unquote flavors of hail. We could go back and look at even some of the alternating growth regimes since we have all these images of hailstones. And it's something that a student, so for the students out there, if there's anyone looking for intern opportunities, please check us out. That would be a really neat project that somebody could undertake with the data that we already have. So really good question from Scott there.
So I'm going to interject my question then, because it's somewhat related, and then we'll get to one more question that we had here in the queue. And mine kind of comes down to, as a weather service forecaster, I've played a lot with MRMS and dual pole data now, and as we spend a lot of time looking at that in the context of what can we see as far as tornado development, what we can see for flooding, for instance, and MRMS has been really helpful in those regards, and then of course dual pole with TDSs. So based off some of what you've seen so far, do you think that we have, well, first of all, have you looked into what radar signatures might be able to correlate to the strongest hail? Not necessarily like in the past, you know, we look at it from size of hail and then implied damage as a result of the size. So has there been anything that you've seen so far that we could use radar data to imply that you could end up getting the strongest hail? And the reason I ask is, I remember a slide you had in there about super cooled water content might actually lead more towards the possibility for it to be stronger. And so I was wondering if you could use something like KDP in conjunction with you know, reflectivity or MRMS, because that would be sort of a proxy for water content maybe, or how much water is actually in, or how many water droplets are larger, and then thus and then there's something we know of in operational world as the KDP hail fail. And so once it gets to a certain point, that becomes zeroed out interaction. So I wonder if there was something to that where we could use some dual pole information to kind of imply that this hail is harder than it, or stronger rather.
That's a really good one, and yeah, that could be a future avenue to explore. You know, from actual hard scientific analysis that we've done, the new dual pole classification algorithms do a pretty good job. I mean, I use them when I'm coordinating in the field, at least to kind of tell you where hail is going to be in a general flavor of size. But I think incorporating both radar observations and some of these environmental cues, especially in the storm relative kinematics, is really going to get us there. I think I'm not sure we'll ever be able to explicitly predict hail size, like the biggest hailstone, you know, within a half inch or quarter inch. I'm not sure we're ever going to get there. And if you talk to someone like Matt Cumgen, he may tell you maybe like in radar linear depolarization ratio, which the 88D products don't have, it may be the only way. But we can take all these, as Trevor, you mentioned, the proxies, and from an operational standpoint, that's probably going to be our best bet and going to be good enough. So that's, I think, a huge avenue for applications. And I'll kind of ramble for a little bit. And as the federal government in the academic world, the government labs, as we develop this kind of foundational science, the private sector is often interested in turning it into those applications. They're used readily across even our industry. So I think if we can get there, it's a combination of both these kind of storm scale environmental observations and what radar can tell us. Out in the field, I mean, the ZDR reduction is fantastic for just giving you a good kind of ballpark idea, and some of the how the KDP field is oriented relative to those ZDR reductions, at least from our use in terms of coordinating the field program, have worked really well. We haven't done a real kind of deep dive analysis in that in a while, really since the dual pole size product started coming out. It hasn't been a huge area of focus for us. But I think you hit a point. I think some of these products you could blend together and use them in that way. So this is all about, you know, going from foundational science to some kind of application and operational type thing. And we talk about operational, getting even into the building science world. It's the same thing. You're going foundational research to some useful application.
Yeah, and so in the operational world, the future of the operational paradigm as far as warnings go, maybe doing away with these binary, here's your box and you're warned within it, and they're going to go within more of like a probabilistic type of plume type of thing. And we talked a little bit about this before, but that I could totally see where that would have influence on where you would have the higher probability of damaging hail versus large hail, and that distinction might make a significant difference to people who are trying to take precautions for that, and whatever partner needs to for different reasons. And so being able to extract, you know, some sort of proxy of this hail is large, but it's also really hard. So we could then maybe add a tag of this hail is particularly damaging and could be catastrophic, you know, something like that. Just thinking down the road with it.
That's a fantastic comment, and true. And I'll touch on a little bit of the insurance side too. The industry in a post-event setting uses all this information to try to understand what the damage should be and how they deal with essentially the claims process. Fraud is a problem in the roofing world, especially after hail events. There's often many roofs that need to get replaced. And unfortunately, there's contractors out there that want to take advantage of people. And often it's folks that we don't, you know, it's elderly folks, and we don't want to see those type of vulnerable demographics actually get taken advantage of by people. So the more we understand about the hail and what actually happened, and some of these things where we have a good idea probabilistically of where damaging, potentially catastrophic hail fell, we can try to hone in, especially as the insurance industry as a whole, to stop the fraud from happening that we know goes on.
Okay, so I asked my question longer than I intended, so I'll go to another person. This comes from Mark Kramer. He asked, what diameter hail did you test to rate your shingles in your testing?
Okay, excellent question. The public-facing results are for 2-inch impacts. That matches the value that the existing test methods rate for. So those products are already tested for that in the old style test. We stuck with that. We have the capability in the lab to test other sizes. So from a standard perspective, we also test 1.5-inch impacts. And although the data aren't public in the same way, we found that most everything should be able to stand up to 1.5-inch impacts in its new state. Now, after it gets really old and brittle, it may be a different thing, but the public facing data is for 2 inches in diameter.
Tanya mentioned that age component. We do have, we have a bunch of, we call them roof farms. They're really just science experiments out across the country. It's essentially small roofs that are out there aging, and we have instruments on them. So we're actually in the process of starting to test one of our first sets of aged roofs that are 5 years old. The program is set to run all the way for 20 years. And we'll actually start to get an understanding of how does performance change with age, which is crucial, because a lot of us, think about our houses. Our roof on our house is, what are we closing in on?
We're on 11 years.
11 years old now. So we need to understand what the performance is with age.
Okay, so we're at 1 hour now. And so for the sake of your time and everybody else, we'll probably come to an end here. So I want to thank both of you for being able to be here, and everybody for asking your questions that was here on GoToWebinar. It seems like we had about 30 people live watching today. And so we'll have quite a bit more as we get this up on our YouTube channel and on nwas.org. And then make sure to subscribe on our YouTube channel if you'd like to get the latest of those coming up. But once we have it up, we'll also put it on all our different social media platforms. And keep an eye out for the next episode of NWA webinar series. That'll probably be starting to have a little bit more of an annual meeting flavor as we get closer to that. But I also wanted to do a shout out that this evening we're also doing our distant social event. And so if you wanted an opportunity to kind of just ask some more questions about what you heard today, Ian is actually going to be able to join us tonight and have a chat with us. So if you want to just ask about Texas Tech, we'll talk about football if you want, or we can talk about a little bit more about the science that we talked about here today. So one more time, I just wanted to thank both you, Ian and Tanya, for being here today and for joining us for our webinar series. So thank you very, very much, and hope to see you again, maybe in another episode in the future.
Thanks, Trevor. Thanks, everybody.